There is a general equation that we use for calculating work, and you might see this covered in other books in a slightly more detailed way. Technically, this is actually going to be a path integral or a line integral, but as this class does not have multivariable calculus as a requirement, we are always going to be dealing with a simplification of this equation in general. So don't worry about the path integral nature of it. If we have a constant force, we're able to simplify this substantially, and we are normally going to be able to simplify it. Normally we'll have a constant force. And the idea in this case is that instead of integrating f over ds, where s is the path itself, if we have a constant force that is constant in both direction and magnitude, then this integral will end up multiplying our force by the distance that was traveled, which we can call delta r. Now technically this is a dot product, and there's going to be a separate video addressing what dot products are if you haven't encountered that before. But one simple way of referring to this equation is going to be the magnitude of our force multiplied by the magnitude of the displacement multiplied by the cosine of the angle between them. And this picture I think is fairly helpful, that nominally we would talk about a force that's pointing in some general direction and a displacement that is in a general direction s. Now they're not necessarily in the same direction, so we would consider the angle between them, theta, and then the displacement here is just from your initial position to your final position. So you have a vector, which is your force, a vector, which is your displacement, theta, and your two magnitudes. So that's how we're going to calculate work. Now what you notice is that work is depending on a force and a distance. So work is inherently coming from forces, and I'm not going to be going into many of the details regarding work because I find it more obvious to talk about potential energy, which is chapter 10. So we will think about work when we're talking about external forces that can't be simplified down to a potential energy. So that might include, for instance, a person pushing. And this situation shown might involve a cart being pulled up a hill, but the person pulling it is actually pulling on a rope that is upwards. So the person isn't pulling parallel to the hill, they're pulling slightly upwards as well. So this would represent then the work done, which we will relate to a change in energy. So in general, work is going to be equal, as I said, to our change in energy. And this is actually kind of a preview for chapter 10, so some videos that will be coming later. And in this case, we would specifically say that this is an external force, so the external work done is changing the energy in our system. And the system energy is going to involve many different types, which we haven't talked about yet. So what that means is right now, we can only talk about a change in kinetic energy. So I find it, again, not that useful to only think about kinetic energy and work, so I'm not going into the details so that later we can really think about the whole picture. But what's helpful to think about this is in terms of forces and velocities, which you hopefully already have a sense for kinematics. So imagine a situation where you have a particle moving in some direction and you apply a force in the same direction. If that is the only force we need to worry about, then clearly our particle is going to speed up. And you can think back to Newton's second law, that our force is in this direction, our acceleration is in that direction. But now if we think about our energy model, in this case then we have increased the kinetic energy because it has sped up. And if we flip all of our vectors around, the same thing is true. So when you apply a force in the same direction as the displacement, remember that this delta S or delta R is the displacement that it's speeding up. And the displacement in this case is caused by it already, our particle, our object, already traveling in that direction. Now a different situation is that the particle is still traveling in the same direction, but now you apply a force in the opposite direction. So this is an acceleration vector that opposes our velocity vector, and that's going to result in the particle slowing down. So that's actually now a decrease in energy and negative work. So work is negative when your force and your displacement are in an opposite direction, and that results in your particle slowing down. So your change in kinetic energy is negative. Your final is smaller than your initial. If your particle doesn't move at all, If there's zero displacement, work is zero. You haven't changed your kinetic energy because your initial kinetic energy and your final kinetic energy are both zero. There is a nice tactics box in the book that goes through this for some different angles as well. So that previous picture was mostly just thinking about parallel and anti-parallel. And now there are three broadly similar, or three categories to talk about. The first is when you have positive work done, and that's going to be, again, when force is parallel to your velocity, such that your displacement and your force are in fact parallel. Another option is when your force and your displacement are actually going to not be exactly parallel, but your angle is less than 90. So you can see that part of your force, you have a component of your force that is in the same direction as your displacement. Now, one thing to be careful about in this situation is that you wouldn't actually expect your velocity to stay only in this horizontal direction. If you were applying only this force and we thought about nothing else happening, you would actually expect your particle to curve a little. So when we're talking about work, we're not talking about the net force, we're talking about a specific force. So what that means is in this situation, if your velocity is staying in the horizontal direction, but we're applying a force that has a component that is not horizontal, clearly this can't be our net force. There are other forces at play. So definitely look at examples for that. Later on, when we talk about energy more fully, we'll definitely look at some of these situations. But again, pulling a rope, pulling a box up a ramp, for instance, by a rope is a good example of this, that even though you're pulling upwards, there are other forces such as gravity at play. So if your force and your displacement are in fact perpendicular, then you actually do zero work, and that's because cosine of theta, cosine of 90, is equal to zero. Finally, you have a situation where either it's completely anti-parallel or there's an angle where it's greater than 90 degrees such that your force has a component that's anti-parallel. And in this case, you are transferring energy out of the system, meaning that you're decreasing the energy of the system. It is important to recognize the two categories of situations where zero work is done. This means that you have a force, but you're not actually changing the energy. One situation, as I mentioned previously, is where theta equals 90. This can happen in two ways. One is actually circular motion. That circular motion, you have a constant speed, however, you're always applying a force. The second situation is where force is perpendicular to velocity. And again, a good example of that might be a box that is sliding across the floor at constant speed, but I'm holding it by a rope and lifting up slightly. If it's not actually traveling upwards, but traveling horizontally, there's not actually any work done. Finally, if there's no displacement. So this picture shows a person pushing on a wall. So if the wall isn't moving, the person isn't actually doing any work. So you can apply a force to an object without actually transferring energy. So it's important to recognize these two situations.